Okay, so you know how last video I decided to make a practice problem video and said I wouldn't make any practice problems for Unit 5 because, there wasn't much for Unit 5. Well, yeah, I lied. Yeah, there's actually one more topic for Unit 5. It's universal gravitational potential energy, as you could probably guess from this video title. And yeah, I chose to make practice problems because, why the heck not? There's 5 this time around. It's definitely not as many, but when you combine it with the 2 from the video, it still adds to the 7, which has kind of become my basis number. Anyway, yeah, getting into universal gravitational potential energy. You know that the formula for like the normal gravitational potential energy is mgh. M is the mass, g is the gravitational attraction or acceleration due to gravity. There's multiple ways to think about it. H is just the distance from like the surface of the planet, right? We also know that there is a formula for this little g here. Little g is equal to big G times the mass of the planet divided by r squared. Now, this formula of mgh, it works fine when we know g is constant. Because, for example, when we're on like a planet, adding a couple more meters to your height isn't going to change little g by a significant factor. Like r in this formula here, it's already probably in the millions, if not the billions. So tacking on a couple more meters really isn't going to change anything. But when you're out in the depths of space, distances are vast. So like uh some changes to R can have major ramifications on G. And once you get to those distances, the basic formula of MGH, it doesn't quite make the cut anymore. Which is why we have a formula for universal gravitational potential energy, denoted by this little big G for, I don't know, universal, I don't know. But it's just to like make it distinct from the U sub little g. This is equal to negative gm1 m2 divided by r. Now here you might be thinking, that's oddly similar to Newton's law of universal gravitation. Like, did you mix it up? I can assure you I did not mix it up. So the m in this in our original gravitational potential energy, that m, it kind of just becomes m1. The h, it just becomes r. It's h and being the height, or being the distance between the two center of masses. It really doesn't matter, right? When you chunk all of this together, we end up getting that ug is equal to m1 times gm over r squared. I'm going to denote it's m, not m sub m, m sub 2, just to indicate that it's m2 times r. Why did I put the 2 down there? It's squared, not a subscript. And, I mean, the square still cancels out. But eventually we get u sub big G is equal to gm1 m2 divided by r. Now here you might be realizing I put a negative when I first introduced this formula. Why is there a negative? Well, there's kind of like two explanations as to why there's a negative. The first one is that the line for like the h equals 0, the basis line, it's set at when r is equal to infinity. And because every distance is less than infinity, everything must be negative for universal gravitational potential energy. The second explanation personally makes a little more sense to me. Who knows, it might be different for you. But universal gravitational potential energy, it should be 0 at r equals infinity. Because like when objects are infinitely far away, there isn't any gravitational attraction between the two objects. Because, for example, like in this formula for little g, when r approaches infinity, g approaches 0. You could write that with limit notation, but I'm too lazy for that. And also, I just don't want to do that. However, as you logically think about it, like, as the distance between two objects increases, universal gravitational potential energy should too. For example, like, in our basic formula, the higher above the surface you are, the more gravitational potential energy you have, which intuitively makes sense. And for example, if I was going to sketch a very quick graph of the universal gravitational potential energy in 0 and r, I mean, we know it has to taper towards 0 as r increases, right? However, as you can see here, if we approach from the top, then it's decreasing as r increases. When we approach from the bottom, it increases as r increases as well. This is what we want. And since all of these values down here are negative, that means that universal gravitational energy has that negative sign in the formula. Let's do a quick little practice problem. Here, like I said, it's going to be pretty quick. Nothing too fancy. Let's say I have a object of mass m. Another big object here, we'll say it has a mass of 6m. And the distance between these two, we'll say it is a distance of 3r. What is the gravitational potential energy stored between these two planets? Alright, gonna assume you've given it a shot. This problem is quite simply a matter of plugging and chugging numbers. We have our formula, U sub big G is equal to negative G times M1, M2 divided by R squared. So we have negative big G times M times, why is there a line there? Times 6M divided by, we have 3R squared. This simplifies to negative, oh, no, there is not a squared. I made a mistake. That's a common mistake with universal gravitational potential energy. It's possible to just confuse it with Newton's universal law of gravitation, and you might think, oh, I should square the distance like I just did there. Don't square the distance. That's a mistake. It's a pretty common one, too. But I guess I can't say anything because I made the mistake, huh? Anyway, this simplifies to 6 times G times M squared. Oh, I don't need a multiplication dot there. Let me erase that. Okay, now I have to erase this whole thing because that annoys me. Is equal to negative 6 gm squared divided by 3r. Do some canceling, and this is equal to negative 2 gm squared divided by r. That's the universal gravitational potential energy stored between these two objects. So yeah, this one's a pretty simple video, pretty simple topic, but like I said at the beginning of the video, more practice problems are available. They will be linked in the description. As always, they will also have answers and explanations attached to them. Yeah, I'll see you next in Unit 6. Give those practice problems a try. I'll see you next time.